Hi guys, so earlier we saw about different types of number systems. Now what we are trying to do is we are trying to convert the number systems to decimal values. So that's going to be one of the things we need to know. So it's like I will start with an example of binary, then we will move along how things happen. So let's say if I'm 101. So in order to convert this, so we already know that this is actually 5, but we have to know how the actual conversion works. So it's like 101. So as we have seen in our decimal system, that 23 is actually 2 into 10 raised to 1 plus 3 into 10 raised to 0, right? So similar to that, this 101 is like 1 into 2 raised to 0. I'm actually multiplying all of the positions with their weights, and 0 into 2 raised to 1, and this represents 1 into 2 raised to 2. So in order to get the corresponding decimal value, we have to just do decimal addition. That's like this is 4, right? 2 raised to 2 into 1 is 4, and this is 0, and this is 1. So this is actually 5. So that's how we convert binary into decimal, by multiplying it with their weights and doing binary addition, decimal addition. And similar to that, if we think about any hexadecimal number, let's say if I do like A5, so if I try to convert this into decimal, so this will be 5 into, the base is 16, so the base is denoted like this, A15, the base. So each position will have its own weights in terms of its base. So the least significant position will be having, the weight is like the base raised to 0, and the position after that will be having A into 16 is to 1. So we know that A actually represents 10 in decimal system. So in order to multiply this, for decimal multiplication, we have to convert this into its decimal equivalent. So it would be like 10 into 16 raised to 1 plus 5 into 16 raised to 0. So if I convert this, this is actually 5, and this is actually 160, doesn't it? So A5 can represent 165. So if you think about it, as the base increases, the amount of value that can be contained in a particular symbol increases, and that increases our ability to do computations significantly. That's why I said in my last video, using binary system is actually a bottleneck for our computers, but it has been tested and experimented, but it's really hard to hold more than 2 levels using electric signals, and that's where the bottleneck comes. But if we are able to represent more numbers in a compact position, then that would be really great, and that would actually increase the computational power of our computing engines. So this is 165. So to generalize this, we have to generalize everything. So if we generalize it, okay, I'm trying to generalize everything. So it's like base determines the quantity that is holded by each symbol. So if I say I have base 2, the symbols will be 0 and 1. Or if I say my base is 10, my symbols will be 0, 1, 2, 3 up till 9. So if I say my base is x, my symbols can go from 0 to x minus 1, isn't it? And so I'm trying to generalize this. Let me take a new page. If I say I have a number which is base x, which is having n symbols, so it would be like the largest quantity that this particular position can hold is x minus 1. That is the largest symbolic value, and here it would be like x minus 1 into the base raised to 2, and it is the next one will be x minus 1 into x raised to 3. The final position will be like x minus 1 into x raised to n minus 1. And if I add all these quantities, I would get the decimal equivalent. So let me take a new slide, and if I think about it, it's like x minus 1 into x raised to n minus 1 plus x minus 1 into x raised to n minus 2 plus dot 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 x minus 1 into, let's say, x raised to 1 plus x minus 1 into x raised to 0. So if I take out x minus 1 from all of this, it's like taking out x minus 1. If I take out x minus 1, it would be like x raised to n minus 1 plus x raised to n minus 2 plus dub x plus 1, isn't it? So this particular thing is a series, and if you remember your old lessons from high school, it's like a plus r, a plus r square, sum of a geometric progression, dub a raised to r raised to n minus 1. It's like a into r raised to n minus 1 by r minus 1. So if we use that over here, I can get something like x minus 1 into, say, x raised to n minus 1 by x minus 1. Okay, so if I cut both of this, it's like x raised to n minus 1. So what does this particular result signify? It signifies that if we have a digit with n positions with base as x, the biggest value we can get is x raised to n minus 1. So it's like No, it's really obvious if you think about it. It's like, if I have two positions, and maximum position I can put on this is, maximum value I can put on this is 1 if we have a base 2, and this actually represents 3. If I do something like 2 raised to 2 minus 1, that's actually 3. So if I have n positions, let's say if I have 3 positions in binary, the maximum value I can get is 1 1 1, which is similar to 2 raised to the number of positions, that is 3, or which actually is our n in x raised to n minus 1. That's set. And if we think about it, if I have 3 positions in decimal system, the largest number I can do is 999. It's similar to the base raised to the number of positions minus 1, that's 999 itself. So we have actually derived a formula which says that if we have a number, or if we have 3 n positions with base x, we can actually have the worst value as, or the biggest value as, x raised to n minus 1. And that's a big result. If we use this result, we can get a lot of answers to a lot of questions. So if we think about it, it's like, let's say if the question is like 531, so what's the maximum number of bits that's required, or the minimum number of bits that is required to represent 521? It's like, maximum number of bits to represent 521. I can do something like 521 equal to 2 raised to n minus 1. So it's like 2 raised to n is equal to 522.